We're now moving into a different business model. We have Chris Bradley from Matter Bioworks here to join us. Hey, Chris. Welcome, come along. And Chris is going to talk to us a little bit about the way that his organization is approaching longevity, not only with clinical development, but also corporate structure. So, Chris, thank you.
Awesome. Okay, so thanks for having me. So, Matter Bioworks, we're a longevity holding company. And just to kind of kick it off, I mean, we've heard a lot about the hallmarks of aging and some of the results of aging, the pathologies of aging. Our approach is a little bit different. We're trying to pursue it from a first principles perspective. And what that really means is trying to find what's the most upstream possible driver of as many of these pathologies as possible in aging. And so what we really see it as is around this concept of the information theory of aging, which you've probably heard of. Really pioneered, I think, primarily right now by David Sinclair. And there's really two parts to it. There's a epigenetic part, so loss of information and epigenetic drift leading to a lot of downstream problems. And then there's another part, which is loss of information at the genomic level, also leading to other problems that need to be addressed. And while you have a lot of investment right now on the epigenetic side, there's not as much focus on the genomic loss of information, and that's really what we're laser focused on. So what does that actually mean tangibly? So you're probably very familiar with this. DNA gets damaged all the time. That's just part of being alive. It's endogenously and exogenously being damaged all the time. And most of the time it's repaired with no problem at all. But occasionally you are getting mistakes that are incorporated and invisible to the body. We call those somatic point mutations. There's also structural variations, but primarily somatic point mutations are what are occurring when this process doesn't work well or not perfectly. So why do we care? Well, there's a lot of research coming out. This has been a hypothesis for a long time, but there's now new research coming out really linking these somatic mutations and their accumulation to the process of aging. So here on the left, you can see that all of the major tissues that are examined in humans accumulate these somatic mutations across the lifetime. And then a question that came out of the Martin Carrena lab at the Wellcome Sanger Institute, which is on the right, is they examined 16 different species, so whales, mice, dogs, lions, giraffes, humans, and they asked a simple question: how many somatic mutations, how many of these point mutations are at the beginning of life and at the end of life, and how do they correlate to lifespan? And what they saw is what you see here on the right. So every single organism that they tested, whether it was a whale or a mouse, had between 2,000 and 5,000 of these point mutations per cell at the end of life. And the speed at which they actually acquired them is correlated to their lifespan. So a mouse will get those mutations, those thousands of mutations, in 3 years, and a whale could get them in 200. So this is it's a really, really strong correlate to the aging process. And not necessarily causative, right? That's still, the jury's out on that, but the correlation is very strong. So why do you care? Well, even if, and this is, again, we don't know exactly what the core drivers of aging are, but let's say they aren't. They are definitely drivers of age-related pathology. So as you can see here, this is just a combination graph. The clearest consequence of these somatic mutations accumulating is cancer. It also is implicated in cellular senescence and a whole range of other issues. So even if you live long enough, you're going to get some form of damage from these somatic point mutations. They need to be addressed. So effectively, what we want to do as a holding company, Matter Bioworks, is we want to bring you back to baseline. We want to get your genome back to the pre-mutated state. So what does that actually look like in practice? Well, there's 4 areas of intervention that we've identified, and they're listed here. So the idea is you need to read the genome. The ability to actually know what those point mutations are, and they are different in each cell, that's a new technology that's emerging. So the sequencing capabilities to actually do this is relatively new. So that's one key area. Repairing the genome more efficiently is the best. So if you can avoid them from emerging to begin with by optimizing repair or upregulating repair, that would be great. If they're there, reverse them, get rid of them. And then finally, there's a lot of instances where it's too far gone. The cell has too many of these mutations, too much noise in the system, and instead of trying to reverse them, just get rid of it, right? And we call this cancer, we call this senescence, and realistically, there's probably a whole set of subgroups that don't have names yet that are also pathological or pre-pathological. And so our our subsidiary companies are focusing on these areas specifically. So we have Mutagen Tech, Spell Check, and Loki, and we have one that we're incubating around the repair. And of course, this is a gigantic presentation if I were to walk you through all of them. So today, specifically because we're in the clinical track, I'm going to be focusing on Loki, but I'm happy to talk about the other ones as well. Specifically, Spellcheck Bio is co-founded with George Church and is focused on a new editing mechanism to address these somatic mutations. So we're really excited about that. So I'm happy to talk about that more later offline. So Loki, what's Loki doing? So one of the consequences of these mutations isn't just cancer, but as we age, the senescence of the immune system reduces your naive T cell population, actually making it harder to fight the cancer when it's emerging around the same time. So this is a key hurdle for any type of immune oncology intervention. And as we heard with the previous company, with Lift Biosciences, this is a moving target that's being targeted by an immune system that's less capable of actually reacting to the cancer. So what we're doing is we're bypassing all of those mechanisms of training the cells, your immune cells, against cancer, and we're actually making the cancer look like something you've already had a vaccination against. So we're redirecting immune cells to kill cancer directly. So what does that actually look like? So the way to do this is you have to get delivery into tumors specifically, and then what we're doing is we're making those tumor cells look like tetanus. We're not only doing tetanus, but tetanus is our first example. So your body says, well, I know what tetanus is. It's bad. I'm going to go ahead and kill that. And by the way, you just got rid of the metastases in the primary tumor and not the tetanus. So how do we do this? So we deliver the payload into the tumor cells. They express tetanus antigens. And then finally, the memory T cells to tetanus from your childhood vaccination are reawakened and kill those cells. It's a fundamentally different approach to immune oncology. How do we effectuate this in practice? So there's three key areas. So the vehicle we're using is an attenuated bacteria. It's a Listeria vector. It has very specific properties in the way we've engineered it, where it selectively infects tumor cells in the tumor microenvironment. And it actually loves metastases as well. So it's a really important intervention for any metastatic disease. It gets there through what we're calling myeloid-mediated delivery. So one of the hallmarks of cancer are myeloid cells that actually attract to the tumor and suppress the immune system around it. You can think of it like a stealth coating. And what we're able to do is we're able to actually hijack those cells and hitch a ride to the tumor cells. So think of it almost like a Trojan horse strategy. So it's a really key part of our specificity. And these myeloid cells love the Listeria that we've developed. So they actually attract to it and eat it, and then we hitch the ride to the tumor and to the metastases. And then finally is the payload. So you can actually deliver all sorts of things, and it's something we're pursuing, but primarily for our purposes here and for our clinical trial, it's a tetanus antigen. And those tetanus antigens, again, are exactly the same antigens as what you've been vaccinated against as a child. So children get these currently, so they're very safe. So I think really importantly, what's the data? So our lead indication for this is they're an all-in-solid tumor. This is in advanced metastatic pancreatic cancer. And we are initiating or about to initiate our phase 1 clinical trial in advanced pancreatic cancer. So this is our preclinical data. So you can see here on the left, this is the before and after effect on both the primary tumor, but critically also the metastases. So unfortunately, especially in pancreatic cancer, for 80% of all patients, it's diagnosed in stage 4. So it's already metastatic, it's already spread. So it's great if you can address the primary tumor, but what really kills you are the metastases. And you need an answer for that for advanced pancreatic cancer. So we're really excited about the results in metastatic liver cancer, or metastatic pancreatic cancer. And then on the right, it's not enough to just have efficacious reduction, but you also want it to actually increase survival. And that's what we're seeing here after single treatment, about a 43% increase in the median survival. We also see this in various models of pancreatic mouse. So the first one shows you is what's called KPC mice. They are transgenic. These are the syngeneic panko2 mice that were actually mentioned earlier. Same thing, you can see our therapy on the far right here, drastically reducing both the tumor weight and the metastases. We also tried it in a different model. So we tried this in advanced ovarian cancer, so a different indication. Again, we see extremely long survival rates. These are Kaplan-Meier curves, which if you've ever seen them, they're usually not this obvious to read. You see a lot of overlap ordinarily. These are clearly different. There's a clear effect given what we're doing. And then what we asked is like, okay, well, how much longer can we keep these mice going? These are mice that are designed to get cancer. There's no curing these mice. Eventually, they will die of cancer. They keep generating new cancer. So we just kept dosing them, and we did a second dose and saw even further extension of survival. This is about an 83% increase in survival after a second dose. We're now doing our third dose, so we're really curious how far we can take this with these mice who are very sick. So really exciting data. I don't have time to go through all of it, obviously, but we have efficacy, safety, survival, tox, all of our pathology, and we're now moving straight into the clinic with advanced pancreatic patients. We have an amazing team, not just focused on this, obviously. As I mentioned, we're co-founded with George Church and also with Jan Vij's lab at Einstein, as well as Dr. Gravekamp, who pioneered the work with Listeria, as well as a ton of great advisors. And we're currently raising the seed round for the holding company right now. And I didn't get into the other assets, but one of the benefits that we have is we're focused very narrowly on this information preservation question, and we have a set of assets at different stages. So one's in phase 1. One of them is actually in the market right now, our sequencing company, and then we have some proof of concept work coming on for our editing technology. So thank you very much.
Thank you.